Welcome back to another HVAC-Engineering-Techie training video. Today's training video is on electrical lighting systems. It's a video that explains what lighting systems are in a building, how they're constructed, what their components are, and how we utilize them. So this is another series in our electrical series. So we're basically going through every building system in a building, all the technical systems, including HVAC. We talk about engineering, construction, equipment systems, test and balance and controls, electrical, plumbing, fire alarm, everything that's a technical system in a building. I really appreciate you being a subscribing member. If you're not, boy, I'd really appreciate if you become one. All you have to do is hit that subscribe button down below. Give me a thumbs up if you like the video. All of those help me because Google uses that to evaluate my videos. Now, those are all free, cost you absolutely nothing. So hopefully you'll do that. Either way, thanks for watching the videos. Let's get started on electric lighting systems. The first thing, I just want to review the videos we have available in the electrical training series. I know you may have seen this already if you've watched the other videos, but we'll go through this just in case you have not. D10 is electrical system design. It's actually for non-electrical engineers. It's basically design light. D11 is electrical lighting design, same thing, design light. Electrical motors and drive systems. S50 is basic electrical for commissioning. S51 is electrical power distribution systems. S52 is critical electrical power systems. And S53, this video, is on electrical lighting systems. S54 is electrical safety for commissioning or for anybody that's dealing with electricity. CX9 is technical CX for electrical systems, part 1. And part 1 is everything to the end of the pre-functional test. CX10 is the second part for commissioning, and it's everything after pre-functional test, which includes the functional test, is what's the most important part. So those are both for commissioning. So definitions of lighting, we'll run through these definitions. They're just helpful to have knowledge of so you can understand some of the language featured on. So standard candle is a candle that emits a uniform luminous intensity in all directions of one candle power. It's just a unit that they've established so they can measure against. LED is a light emitting diode, is a semiconductor diode which glows when a voltage is applied, and that's what gives us LEDs. A lumen is LM is the semaphore, the rate at which lumen's flux falls on a 1 foot square surface of a unit sphere. One standard candle equals 12.57 lumens. Again, these are just, now there's a little confusion sometimes in lighting. Most of it's done in metric, but it's also done in inch pounds, and so we have to make sure we understand the difference between the two. So lumen is actually an inch pound. Foot candle, which is the English system, the ratio of the total lumens of inch evenly distributed over a surface to the area of the surface in square feet. 1 foot equals 1 lumen per foot squared. Lux is the metric system, same measurement, but it's called lux. And it's 1 lux equals 1 lumen over a meter squared. So basically a lux. Reflection, the light which strikes a surface and is reflected. Diffuse reflection exhibits the equality in all directions. When it's diffuse light, it's not going to glare or bouncing back and forth. Transmission, materials that permit the passage of light and images. Absorption, material that does not reflect light from the surface, it absorbs it. Refraction, medium that bends the light that passes through it. HID is a high-intensity discharge light source. Halogen, the halogen lamp is an incandescent lamp consisting of a tungsten filament sealed in a compact transparent envelope that is filled with a mixture of gas, such as iodine or bromine. The high temperature of the light provides high luminous efficacy and a natural color temperature. So we'll go over all this when we get into what type of lamps are out there. All right, lighting power distribution. The power for lighting is distributed just like any other power source in the electrical system. So normally we prefer that each load within a system be sub-metered separately, so the operators have a chance to actually manage that power. So the main deal is that, if you'll see here, this is a piece of switchgear where the main power comes from the utility. And then we distribute that power with subsections within the SES. And you'll see this one, picture one here, has a feed going up to a high voltage panel, a 480 volt panel. And this is lighting load. And then that lighting load goes from this panel down to a transformer to a low voltage, a 208 120 volt panel, lighting again. And so these two panels feed the lighting to this particular facility. And we have these lights in the ceiling that are normally something, well, it might be 277 lamps. It'll be up here on this higher voltage, and this may also do the parking lot lights and all that stuff. And that means that by 1 meter right here, we can meter all the lighting in the facility. Now, there are two types of lights. One is there's normal lighting, which this would be, and then there's emergency lighting, which would be off somewhere else here. And emergency lighting has to be fed to a separate panel because the generator backs up that lighting differently than it does to normal lighting normally in a facility. So that's why we do that. Power distribution equipment still has the same equipment, still has the main switchgear, still has sub feeds. Everything's the same. It's just feeding a different type of material. Wire and raceway system is the same. The grounding system is the same. The backup power systems are common, so it's still the same. Metering systems. Now, I said we'd like to have the electrical on a meter. You can do it different ways. You can have several panels throughout the building and meter each panel separately. Or you can do what I did here and put them together and meter one sub-feed deal. And what we're really trying to get at is we'd like to have the plug load and the lighting load metered separately and the HVAC load metered separately. Now, the whole key here is being able to see what energy the HVAC system is using, because that's the one the operators can affect the most. You can affect lighting by changing the schedule, but normally that's not within the purveyance of an operator. That's done by management. And once the lighting schedules are set, he has very little change. So he can't affect that very much. So what we really want to do is make sure he can see the HVAC. If we don't have sub-metering and we just allow on the utility meter, then he sees the whole bundle at once. And the HVAC appears to be really diluted. So any change he makes will be a very small change in the total energy. That's why we like to have it sub-metering. Now, to do that, the electrical designer must lay the system out separately. If we want to meter the lighting load separately, we need to lay it out such that we can do that. Now, again, you can, if you take the lighting load and mix them up in these panels down here, there's no chance to meter it effectively. So basically, we need to have separate lighting panels and separate power panels and separate plug load panels. That's why the designer has to be involved, so he can separate those loads so we can actually measure them adequately. And of course, power management systems, and there's normal lighting and emergency lighting, and I explained the reason is because emergency lighting has to be on standby power, where normal lighting does not. So lamps, electrical lighting lamps. So first thing I want to talk about is color index. Now, all lamp sources have a different color. Correlated color temperatures in Kelvin. So it goes from 1,000 clear up to 9,000. But normally what we see is somewhere between 2,500, maybe 2,400, up to about 6,500, which is the starkest light from outside. And we want to be somewhere in between. And normally what we are is a color match the same space. So in other words, what I'm trying to say is you have a big space, please keep all the tubes the same color. Drives me absolutely crazy when I see maintenance people who don't know that and buy just a light bulb, don't pay attention to its color, and you get all the sprinkling color differences throughout that. Now, I have known some designers that do it on purpose. Still drives me crazy. Don't do it. Pick the one. So I normally pick right around 3,000 for warm white. It's a yellowish. 4,000 for cool white. And then 5,000 for bright white. I never use 5,000 for anything unless there's some intense need for having a real intense light source, because it's just too bright. Normally we see over here that you'll see that the cool white is 4,100 to 4,600. Warm white is 3,000 to 3,500. And then bright white has appeared. So what happens is this light all reflects colors differently in the space. If you take a 3,000 warm white, which I like because it's more comfortable than the blue light, or the ultra white light, it's more comfortable. But red will look much brighter under this cool white or this bright white. This bright white, it'll really bounce red. This one will be somewhat subdued. That's because of the color of the light affects how you see colors. Also, the color of the light affects how your body actually deals with light. Now, remember, the reason outside light has these colors is when the sun comes up in the morning and the rays of the sun have to travel a long ways through the atmosphere. It's a warm color. The atmosphere changes the color and allows more warm length of radiation through. As the sun goes up in the sky, that gets less atmosphere, and it gets brighter and brighter and brighter till about noon. It'll be up around 4,800, 5,000, and then it will begin to go back down. In the evening, it's 3,000. So your body knows the difference between 3,000 and 5,000. It definitely knows. So if you're getting ready to go to sleep, you do not want to be in 4,000 to 5,000 Kelvin lights, because your body's saying, wow, I've got to stay awake. I got to be here. The cool white, this is why they tell you not to look at blue lights or read really bright computer screens before you go to bed, because it revs your body up. It'll be cool white. My thing about the color is, in my opinion, the warm white is more comfortable to be in a building than the bright light. So that's just my opinion, but that's kind of what the colors are. Incandescent lamps. Now, they've, in the recent years, the government has basically said that we want to stop the manufacturing of incandescent lights and we want to go to LEDs, which basically we have. LEDs are everywhere now, but you can't actually stop incandescents because we actually need incandescents. Two kinds of incandescent: standard bulbs, which would be these normal bulbs you're used to seeing, and halogen bulbs, which would be either this kind of bulb or else a long, skinny bulb that's got this gas in it and halogen. Now, the difference is high CRI, which is a color rendering index, is halogen. And that's why when you go and you shop at a real fancy jewelry store, or you go to a cosmetic store, or you go to a car dealership, you'll notice their lights are all halogen lights. And the reason is because everything looks really good under halogen lights. And under LEDs, not so much. So basically, halogen are going to be around for a long time to come. And that's an incandescent bulb. They don't last as long, but they sure make things look good. And I've gone into some stores like Penny's or whatever, a national brand, and you walk around the store, you'll see LEDs everywhere. Then you get to the jewelry counter, you'll see halogen above the counter, and that's because it makes those gems pop. So that lamp is going to be around for a long time. And you can see it comes in different flavors. This is a par 30, this is a par 20, all halogen. This is a halogen studio bulb, and this is a 50-watt low-voltage halogen, and you will see these everywhere. This happens to be the typical indication lamp type. And here's some general stuff, and you'll see the lifetime, 752,000 hours. This is the burn life. And the reason is because the normal incandescent bulbs use a filament, and that filament gets heated up, and it emits photons when it gets hot. And the problem is that when you turn it on, turn it off, you're actually shocking that metal filament, and eventually it will break. And that's why you remember the old-time light bulbs. You look up and you'll see it broken, you throw it away and buy another one. And this goes all the way down to different halogens. You can see halogens a lot longer than a regular incandescent. And we have different kinds of halogen depending on the gas. They can change the color depending on the gas they have in there. So the standard halogen bulbs, I don't really remember what gas is in there. It might be iodine and bromine. I'm not really sure. So fluorescent lamps. Now, fluorescent lamps come in all kinds of different sizes and flavors. The original ones were T12s, and you can always recognize a T12 because it's about an inch thick, a nice thick bulb, and I love T12s. And the reason I loved them is because every time I go on a job, especially a retrocommissioning job, and I look up and they got T12s, man, I know I've got a good job. And the reason our T12s are very energy inefficient. And you could do a lighting retrofit and pay for the entire rest of the retrocommissioning project with the money you saved getting rid of T12s. And then T8s for the next one, and they're about, 5/8 in diameter. They're a little skinnier, maybe 3/4. And you could tell they look the same, except they're smaller diameter and they're more energy efficient. So we did a lot of lighting retrofits going from T12 to T8 because you only had to change the bulbs. You didn't normally have to change the ballast. And then there was T5s, and T5s was a big step to get more the same. They wanted to do the same thing they went from going from T12 to T8 by saving energy going to T5, and they did, but it didn't actually catch on. There's a lot of T5 fixtures, but nothing like going to T8s. I'm not sure why. I didn't really get into that, but normally T8s. This is a T8. This is a T5 bent tube. And then there's compact fluorescent, which are the ones that tried to take care of an incandescent bulb. And these were basically fluorescent bulbs, but in such a design factor that they would fit in the place of an incandescent bulb. Now, the lower output due to age, so these 3 to 5 years. Now, one thing about a fluorescent, it does age. And as it ages, its lighting output goes down about 30%. Near the end of its life, it'll be down 35%, which is a lot. So what happens is a lot of people in their facilities never bother to change a bulb until it burns out. And so when you go in to do a lighting retrofit and you change bulb per bulb, same number of watts, big difference in lighting because it was getting dimmer and dimmer and dimmer and they didn't notice. So that's one of the things about age of lighting fixture. Now that's 3 to 6 years. 3 years is it running 24/7. And then 6 years is for it being on 12 hours a day. So that's a normal lifetime for these bulbs. And unfortunately, most people didn't have operations protocols in their facility to change the bulbs every 5 years. That's what I recommended. You have a ongoing program that every 5 years you change the light bulbs in a space to new fluorescents, so you can get over and start over. If you just let them be replaced as they burn out, they'll still get replaced in 6 or 7 years, but the quality of the lighting in the space will be much, much lower. And these are standard fluorescents. You'll see there's high efficiency standard, high efficiency compacts, and you'll see 20,000 hours as a typical life and 10,000 for these. Most compacts didn't last 10,000 hours. And the reason is because there's not only the bulb part, but there's also a little transformer down here. It's their ballast. And those didn't seem to last too long. Especially the first ones made in China were pretty low quality, and they would just fry up. So these weren't as successful as they should have been, only because their lifetime wasn't as good as they should have been. So HID lamps, mercury vapor is a blue or green color, 24,000 hour life. These are big bulbs normally used in high bay fixtures or parking lot fixtures, that sort of thing. Metal halide is yellow or green. It's 10 to 20,000 hours, slightly different bulbs. High pressure sodium yellow, 24,000. As you drive around and see canopy lights, like at gas stations, and you'll notice they're different color. Well, you'll notice they're different. The yellow ones are probably sodium. The yellow or green can be metal halide. Blue-green is mercury. So you can actually see the different colors as you drive around. And then here's their lifetimes at 24,000 hours. Metal halide is 10,000, as we talked about. And, of course, the lumens is part of the design process. You put a bulb in for a certain amount of lumens to get a certain amount of foot candles at the area you want to light. So this is all about what's available. Most HID bulbs look exactly like this. These are some specialty bulbs, and you can get the little A-frame ones, but most of them are like this. LED lamps. Now, LED, if you want to go out and try this sometime. I've just done this lately because I have a house that has some fluorescent light bulbs in the closets. And so I went to replace a light bulb, and boy, it's getting hard to find fluorescent lamps. I mean, they're there, of course, but it's much harder. Almost everything's an LED. If you go online and try to find an LED, a regular fluorescent fixture, hard to find. It used to be everything was a fluorescent, and you couldn't figure out how to make an LED. Nowadays, it's the other way around. So there's standard socket and retrofit. These are just lamps. We're talking about LED lamps. And LED lamps are basically designed for replacement of standard bulbs in a fixture. So there's typical LED lamp data, floodlight, like a 40-watt, decorative tier, exit lights, and that sort of thing. So LED lights have a little issue that most people don't understand at all. And that's the LED junction temperature means what their lifetime will actually be. So this is a little different than a bulb. You know, where a bulb has a filament that lights up, this is not. This has a semiconductor, which, you know, looks like a piece of plastic. And when they put a voltage to it, it glows. And depending on the material and depending on what kind of transistor it is, it will do a different color. And that's why we have red and green and blue LEDs. We do not have white LEDs. The way they make LEDs is they put a bunch of LEDs together and mix up the colors. And so the resulting light is a different color. Well, each of those transistors' lifetime depends on that temperature right at the surface. If you know much about semiconductors, they're made of two different types of material, and they conduct electricity difference, and that's how they get the properties of the circuit. Well, for an LED, they put a whole bunch of power to it. Where a regular circuit, they put just a little bit of power to it. Well, an LED, because they're trying to produce light, they put a whole bunch of power to it, and that causes temperature where those two things meet. And the higher the temperature, the less the lifetime of the bulb. And that's why, up till now, most LEDs didn't last anywhere near their projected lifetime. And the reason is that in the real world, that junction temperature was much different than it was in the lab, or what they intended. So I've had LED bulbs burn out in 6 months, 5 months, 8 months, just because they should have lasted 5 years. But they didn't, because the different components in it and the LED itself didn't last. So 6 to 10 years, depending on temperature for a good LED, depending on how many hours it's on, of course. This 6 is with it being on 24/7. 10 years if it's on 12 hours a day, a little bit difference. Now, this is an LED fluorescent replacement lamp, and it's a LED that there's different kinds of them, so you have to make sure which one you're plugging into your fixture. Most of them originally required different ballast, or that the ballast be removed. Nowadays, they have them that'll just plug right in with the ballast that is there for the fluorescent one. So they're making headway on what's replacement here. The biggest problem is making sure these are the same color when you put them in and buy the last. So this T8, now you'll notice that this is a 32-watt replacement. It only draws 17 watts. That's why these LEDs are much more efficient. When I first started years ago in design, as I would design a mechanical system, we would normally have 2.5 watts per square foot in lights, just an assumption. And we'd have about half a watt in plug load, not much plug load. Nowadays, it's totally different. Nowadays, you get under a half a watt in lighting because of LEDs, and we get way over 2.5 watts because of computers. So the plug load has gone way up, the lighting load has gone way down. It's all about seeking efficiency. So nowadays, there is another thing about, I talked about doing LED retrofits. Like you can change these bulbs for fluorescent. You can change these in par fixtures. You can get small ones in par 20 and par 10. You can also get standard LED bulbs like this that are actually LEDs, have the ballast down here for the LED. The problem is that you can change these out as we go through and retrofit them. But the main problem is that the amount of light that an LED puts out is normally more than what an incandescent or a par fixture or a fluorescent lamp did. So if you have a room that's been lit with T8 fluorescents, and you just go in and change all the tubes to LEDs, you'll overlight the space, and the space will be much brighter with much more light than it needed. So most of the time when you're switching from incandescent is fairly easy because you can get a bulb about the same lumens out pat, much less wattage into the fixture. But if you're doing a fluorescent change out, it's normally better to change a fixture, because instead of those 2x4 fixtures, you probably only need 2x2 fixtures with LEDs, because they're about 37% more light in an LED than most fluorescent bulbs. So that's why we normally, when we're doing a lighting retrofit, we go back to a lighting design. When in the old days, when we did fluorescent to fluorescent, we didn't need it. We could just replace them and be at the bulb's the same lumen output, and we were good to go. And then we have high intensity lamps with LEDs that replace bulbs that we're using for large open spaces. We have other fixtures. We have decorative lamps. These are actually LEDs. They look like long filaments, but they're actually LEDs. So we see those. We have exit LED lamp conversion kits. Now, the one thing about exit lights, they originally had like Christmas tree bulbs in there that were 40 watts or 20 watts, but two of them are 10 watts. You have four of them, and then you have 40 watts per fixture. Well, LED will be about 4 or 5 watts per fixture, so it's much less. Even though it's not a lot of watts, it's very significant. So when we do lighting for retrofits, we always changed to the LEDs. So electrical light fixtures, incandescent fixtures, incandescent halogen light spectrum. They come in recessed form like this, or decorative fixtures. It's on suspended type fixtures, decorative type suspended fixtures. Fluorescent light fixtures come in parabolic lay-in. And a parabolic was different because instead of just shining really bright at the ceiling, it was dark at the ceiling and the light was forced down and it lit the space adequately, but it had a very low light level because there wasn't a bunch of ambient light above here. So you don't see many parabolics in LEDs because they don't do that way. They're diffuse light sources. Troffer lay-in, which is a standard fixture you're used to seeing. And we have surface wraparound fixtures that are mounted surface-wise. We have strips that are normally surface-wise. Then we have suspended lights that also have backlights. They shine light up to the ceiling and light down. We have high bay reflectors. So this has a poly-stainless reflector behind the lamp, which forces more light down. We have compact fluorescents, which you talked about, light fixtures that are specifically built for compact like these. You have to have this exact kind of bulb to place in it. It's not an A socket, so you can't change it back and forth. It's designed for that only. So commercial LED fixtures, we have panel lay-in fixtures that look like a regular fluorescent troffer. We have wraparound LED fixtures, looks like a standard fluorescent. And we have troffer lay-in LED fixtures that have only 2 bulbs instead of the 4 like we'd have up here, and even though they'll do near the same amount of light. And then we have linear LEDs. We have strip linear fixtures. And we also have, this is a hanging fixture. This is a can light LED, canopy lights, emergency lights. The emergency lights are basically battery backed up lights that when the lights can be fed from a generator, when the regular lights go out, they come on by the amount of lumens in the space and shine these lights for egress so you can get out of a space. And we have LED backup batteries. Now that you have LEDs, which take such low wattage, we're able to put backup batteries right in the fixture itself. So they have ballasts that include, for the LED, that actually include backup batteries. We have exit lights, and exit lights, of course, come in red or green. And different kinds of exit lights, some with emergency lighting on them, some with not. You have two-sided, single-sided, whatever you need for exit lights. So exterior LED lighting. We have wall lights to provide exterior lighting. We have spotlights. It can be different sizes and what way they're built. Canopy lights that are up for canopies around a building. Parking lot lights. Street lights on our street light poles. And pole lights that are designed to light up areas like industrial areas or whatever. High bay fixtures, we can have either HID fluorescent, high intensity fluorescents, reflecting fixtures, or LEDs. All of these are available now for high bay. Now, what high bay is that when you take a regular light fixture and you look at its design parameters of how it distributes light, it changes by height and width. So normally it looks like a pear normally. And as it goes down, it gets wider and wider, and then it starts drawing in itself, which means the light is diffusing after that point. So most lights don't reach but 10 or 12 feet in their intensity, and then the intensity drops way off. So high bay fixtures are designed to provide light at 25, 35 feet, or maybe 40 feet. So you can put this fixture up in a high bay. And we do that at warehouses. We do that in manufacturing facility that have cranes and things like that. You got to stay out of the way of, so the light fixtures are way high. So this is a high bay HID fixture. This is another one that's HID that hangs from up at the top. Then we have a high bay fluorescent with reflectors to try to get more light down lower. This is an LED that's pretty intense that will put the light down. This is a high bay LED with reflectors, which also helps. And then these are high bays with direct LEDs. They don't look like much, but they're a very bright light source, and they can put out a lot of light. So all these are high bay fixtures. Then there's theatrical lighting, which most of us don't get involved in, but it's really interesting. I've done several projects for Disney and looked at their lighting controls and commissioned some of their lighting controls. Very exotic, very interesting stuff. And then lighting is either HID or LED. It can also be incandescent, but not much of that left anymore because two things. One, because of the energy, and two, because of the heat. Actors have a big problem when you put a whole bunch of lighting on them, it gets really hot, and incandescent did that big time. New LEDs, not so much. That's kind of a thing of the past. Still can be a problem, but not. So here's a follow HID spot. This is a spot. This is a spotlight that someone actually operates to keep a performer in the spot. And these can be, HID can be, these could go 400 or 500 feet, a long, long ways. Not so much if it's an LED source, but this one, this is an LED spotlight. This is not a follow spot, but it's a fixed spot. This is a candlelight LED. It's a general light. This is a motorized LED spotlights, and these are robotic, so they can actually program from the console to do different things for whatever the stage act that's going on. They can change color, they can change position, many things they can do because they're robotic. And this is an LED floodlight. And you see these different colors, LEDs in there. They can change color. Every one of these pixels can change color, and it can make a different color for the stage. So it can be red, green, yellow, white. It can be anything you want, and it can do it in real time because it's programmable. So lighting control. This is the other thing we have to worry about in lighting, is there's control systems normally, some kind of control system. So they can be controlled from the switch. You can control from a lighting relay. They can be controlled from a lighting control panel. You can have a Wi-Fi breaker control, so you can have basically wireless control of lights. You can have occupancy control, so it's controlled when it's occupied and not occupied. You can have daylight harvesting, which basically measures the light level. And if the area is open to sun, as the sun gets brighter and brighter, it'll dim the lights to use electricity, of course, less electricity. Wired network controls, which are called DALI systems, and those are systems that actually have full network control of the lighting. And wireless mesh networks. So lighting networks can get fairly complicated. And the wireless networks, the fixtures all talk to each other. Wireless mesh networks, the first time I worked on one of those was really interesting because I was with the manufacturing vendor, and he came out and he was programming them. And when he walks around with a laptop, basically I think it was an iPad, and he said, okay, I want this fixture, that fixture, that fixture. I want them to be controlled by this wall switch. And that's what happened because everything in that room was all based on wireless control, and he could program them right there from his little iPad. And I was very impressed. Now, what that means, of course, is if you ever do a remodel, now you can rearrange the lights to a different switch, which is much better than having to tear up the walls to do that. So I was really impressed with that. Theatrical lighting control, which is a huge lighting control thing. So lighting control switches, this is fairly simple. A wall switch, you have a panel that has a circuit breaker in it, leads out to a bunch of lights, and somewhere in there will be a wall switch that turns that circuit on and off. Really simple. You have single switches, which basically is a one-way switch. Switch is open, it's off, switch is on. And then you have three-way switches. So you're going to have two switches, and the way the circuit works, if you look, if this was switches in this way, then if this switch is that way, the load is on, but if the switch this way, the load is off. So what this means is that either switch can turn on the load or turn it off, and that's what a three-way switch is. So you're going to have two switches. Now you can also have more than three, and a four-way switch is basically capable of doing more switches than three. Many more, if you want. It can get very confusing, but it can be. And basically, the four-way switch looks like this. And these are three-way switches on the end. So basically what happens is this allows that circuit to follow, so any switch can turn the load on or off by switching these back and forth. So a four-way switch, it gets a little bit more complicated. And these, you probably have these in your house. But that's basically how these operate. Lighting control, remote lighting relay. Now this would be if you have a circuit breaker that's leading out to a bunch of light fixtures and you want to put a relay in here and control that relay from some control, a time clock or a computer's or a BAS system, whatever. And this is normally done with a latching relay, which means the control simply sends out a pulse and this relay changes position. So if it's on, it'll turn it off. If it's off, it'll turn it on. And the reason they do that is so they don't have to keep power to this relay. Relays that are just standard relays, their lifetime is depending on how often they're on because there's current going through their coil. But with a latching relay, that's not the case. It latches and then it unlatches. And so that's why we use latching relays there. Okay, so that's a latching relay, a lighting relay control panel. So we have our standard circuit breaker panel, and that circuit breaker panel goes through a lighting relay. And so this powers right to this lighting relay, and the lighting relay goes out to the light fixtures, and then we have a remote switch that can control that relay one way or the other. Or we can have a control circuit that comes in that controls a group of these light switches. And this is a lighting control panel, and we do this many, many times. They also sell circuit breaker panels that have this relay built into the circuit breaker. Very convenient, but also the breakers are much more expensive that way. These are fairly pricey. These are really pricey. So we don't see a lot of those that have these built in just because to replace them is not as convenient as going running down to the local hardware store to buy a new breaker. You'd have to order it because they won't have any of those unless they're electrical supply house. Low voltage switching would be this out here to low voltage. Hardwired lighting control. This is occupancy control, so it has this hardwire going out again. It has a wall switch to turn it on and off, but the occupancy sensor can override that wall switch. You can turn it on no matter what position it's in. But this is a motion occupancy control. There's two types of occupancy control. There's a occupied control and a vacancy control. And they control the same thing, but they do it slightly different. So it can be either one. Now, daylight harvesting is basically refers to dimming. What happens there, it has a standard panel. It goes out to a light fixture, has a wall switch, turn it on and off. It also has a light sensor that will dim this fixture when it's on to maintain a certain lighting level that's programmed into it. And that's called daylight harvesting. So DALI lighting control is a much larger system. And this is the power source up here. And these are the fixtures here. This is a computer system, and this is the data channel. This can be wired or it can be wireless. But this is a data channel that goes to each of them. And then it has these control units that are on there that allow switches. So this is a smart switch configuration. So if you've ever been in an office building that has these wall switches that have a whole bunch of options, that's a DALI system. So you punch a scene you want, or you punch in, I want this many lights on, it goes to a controller, and that controller turns on, through this network, turns on what fixtures it wants on. This is a scene controller. So this you could say, I push a button, I want it seen where the lights are dim, it's really comfortable, it's more for a party atmosphere, or I want it for a work session, it's going to be bright, you can have different scenes in here you might want it to have, and that controller does that. And then here you have the light sensor, that's on a separate driver. You can have a motion sensor, those are on separate drivers. So these are the input sensors that you can have, and these are the LED drivers. This might drive a batch of lights, or might drive just one. This is a fluorescent light driver, LED driver, so these are available. And this is what the DALI system looks like. It has switching, it has occupancy control, it has daylight harvesting, all available depending on how you configure this network. And this also allows these lightings to be integrated up the ladder to a BAS system or any other control system, a SCADA control system, because it's just a digital control system. And you can integrate with it so you can see the lighting or control the lighting by more than one source. So that's why they have DALI systems. And scene control. So there's Nlight's a popular one, Watt Stopper's a popular, DALI systems, and there's many, many others, but these are what I like Nlight best. I have done many Watt Stoppers, and I think they're getting better, but Watt Stoppers used to be the best hardware and the absolute worst to start up. It took forever to start. Nlight, piece of cake. I'm not campaigning for them, but basically, in my line of work, this was much easier. But there's many, many others, and they're getting more all the time. So wireless mesh network lighting control, wireless digital addressing lighting interface. There's Zigbee, lead-advanced link, Bluetooth, and mesh technology. Mesh Tech, which is a Bluetooth technology, and many others. But these are the ones that are, Zigbee was the original one, and these others have come out since then, since this Bluetooth mesh. Since Bluetooth mesh technology became available, many different companies have adopted that technology and come into the marketplace. And I'm sure there's many others. And basically what happens there, that the ballast in the light fixture basically have this communication, either has Zigbee or they have Bluetooth or whatever other one they're using capability. And then your switch device has the same capability, so they communicate over this mesh network. And the reason they call it a mesh network is because this transmitter doesn't have to transmit very far. It can be very small, very low power, because every single light fixture has this network in it and every single switch. And what happens is these bounce. So if this switch is a long ways away, it can bounce to other light fixtures before it gets to the one it wants to control. So it may bounce between 10 or 12 fixtures before it gets here, but it will get there, and it has a code only for this fixture. So that's why it's called a mesh network. It will work its way through the mesh. That way your devices don't have to be real high power. They can be real low power and still get the job done. Theatrical control, wired controls, network systems, Wi-Fi systems, normally very complicated and very expensive. So this is a dimmer rack unit to dim a bunch of high-powered lights. You can see it just looks expensive. This is a DMX transmitter and receiver for doing wireless control of lighting system. This is a stage control, allows you to change the lighting and whatever, and program the lighting on the stage. And this is a stage control master unit. So you can have, these are just local, and this could be a master unit. This is a stage control master unit. Now, I didn't get involved in the stage lighting because it's so detailed and so specific, but there are some real specific lighting control systems for stage. Now, normally, a normal lighting control for the building and stage lighting is separated, so you don't have to worry about falling into the stage lighting. And my advice would be is to stay away from it. If in your project has stage lighting, that should be done by a specialty contractor and started up by specialty people. The reason is because their criteria are much larger than your criteria. Exactly how that lights work. There's a whole bunch of programming and software involved, so it can get very expensive and very complicated quickly. But if you have to, it's there to do. So that's lighting systems. I hope that was helpful. It was kind of a rush through everything, but that is basically the world of electrical lighting. If you take the design module for that, it'll explain a little bit about how they're designed and how all those lumens and everything matter. But that's beyond this particular video. So I really appreciate you watching the videos. Thanks for being here. I really do appreciate it. If you have any questions, put them in the comments. I will answer them eventually. I don't do it all the time, but I do it every other week or so. So have a great day, and I will catch you on the next one. Thank you.